Please meet David. Yeah, here you go.
Hi. So, as Dimas said, my name is David. You can find me on Twitter under Halasz David. As you can see, I use my name in the opposite name order, so you can guess which European country use it in this order. I'm Hungarian. And I like to live dangerously. And by living dangerously, I mean I'm going to start a live demo right now. It will all make sense, so I just start the demo. Wait, you will not believe me that I started it because you don't see my screen. Give me a second. So, let's try to zoom it. Scream when it's big enough. So I wrote Vagrant up, it's visible. It's starting the VM. Let's get back to the talk. So it will build like 10 minutes because I need to download like 500 megs from the internet. So please don't download anything in the meantime because otherwise I will have to take the questions earlier. I wouldn't like to do that. So I came here from the Czech Republic, from the town called Brno, which is, if you don't know, famous for beer, which isn't really my favorite. MotoGP. And we had a really famous genetic experiment a few hundred years ago. Not him, another green thing. So Gregor Johann Mendel did the famous first genetical experiment with bees a couple hundred years ago. He was a monk. He was the father of genetics. So I'm a software engineer. I work for a company called Red Hat. You probably heard about it. I'm working on a project called Manage IQ as a former colleague who's actually not in the audience right now. So he would say, yeah, he's here. So he would say, if you have a cloud, we can manage it, right? Yes. So imagine a Rails web interface where you can add credentials to your Amazon, Azure, OpenStack, VMware, Red Hat virtualization providers, and you can manage everything from one single user interface. Pretty easy, right? Okay. So I want to talk about things called remote desktop sessions, and I will show you what I mean by remote desktop sessions. Everyone used Windows, so everyone knows what it is, right? Yeah, and the password is wrong. Anyway, you get the point. You can remotely access a physical or virtual machine screen through the network. And the thing I'm working on Manage IQ are called in-browser remote consoles, which are surprisingly remote consoles in HTML5 canvas. And it's something like this. So you have a browser, and in the browser you can see a Fluxbox virtual machine with one screen running top, showing your processes. In the context of Manage IQ, you have a summary screen of a virtual machine, and you want to access the VM console, and you get a pop-up where you can remotely access the remote computer. It can be physical, it can be virtual, doesn't really matter. If you look at the architecture, you should imagine a VM and the browser. If you don't see something behind me, because I'm having the stuff here, so if you don't see something behind me, just scream again. I would like to have this a little interactively. So the VM runs on a hypervisor or a host machine, whatever you call it, and it provides you a VNC session. if you run VirtualBox or VMware on your computer, you can actually turn this feature on. So you can try this out. There is a VNC endpoint in your virtualization application. Unfortunately, the browser doesn't really understand VNC. The browser can do HTTP and WebSockets, which are a little closer to bidirectional communication like VNC. So you need something in the middle, something, let's call it proxy, that would bridge the two endpoints somehow. So let's talk about the proxy. If you look at the proxy a little closer, you realize that it consists of scary stuff like concurrency and blocking IO and sockets and rec, and we're all going to cover it. So if you look from a different angle, here you have the two endpoints, WebSocket and VNC. Thank you, Dima, for the translation. And you need to read from WebSocket and write to the VNC, and read from the VNC and write to the WebSocket, and translate between the two languages. And if I talk about endpoints, what the hell are those endpoints in programming? How we represent network connections. And if we uncover it, you can see that they are sockets. I was giving this talk in Australia, and a lot of people didn't get the point, and first I didn't understand why. First I didn't understand why, and someone was like, hey, because we have it differently. Whatever. So when you program with sockets, you write code something like this. So here I'm opening the website of a conference, which will be in June. So you open this connection to port 80, which is HTTP. You write something there. And here I have the response, and as you see, it's an HTTP request response. So I get a redirect because it's normal HTTP, not HTTPS, and they are enforcing HTTPS, which is a good thing. You should all do that. Anyway, so this is how sockets work. And if you look at the methods read and write, what other objects from programming are coming into your mind? Yes, sockets are files, but for networking. And if you imagine the old hard drive times, if you're old enough to remember that pre-SSD era, you couldn't survive to writing disk without buffers. So when you write to a file, you actually, or a socket, doesn't really matter, you actually write to a buffer, and that buffer gets offloaded by the operating system. So if you write to a socket, it actually puts the data into the buffer, and when there is time on the network card, there is space on the network card to send the data, the operating system will form packets and send it through. You don't really have to care about IP and TCP and all the things. You just have a file descriptor, you write into it, and that's all. And what happens if there is no space in the buffer? Yeah, it blocks. Thank you. So if the buffer is not big enough, you have to wait. So the operation can take seconds, minutes, hours, depending on your network configuration. So this is why it's called blocking IO. I was lazy for doing the animations for reading, so you have to imagine it. Basically, it's the same, but you wait for the buffer to have some data before reading. So if you call the read operation and nothing comes, it will just block. So if you would like to do a proxy with blocking IO, you would like to, a translating proxy, you would like to do something like this. As both endless loops can block, you need to put them in threads. So here you have the two sockets. You read from one, let's say, 1 kilobyte, translate it with this magic method I will not explain now, and write to the other part. Here is the exact opposite. Does it make sense? Okay. So to overcome this problem of having a lot of threads, because GVL and all the things in Ruby, and not just in Ruby, but in other programming languages as well, you don't really want to fork a new thread for each connection, or two threads. There is a solution called Nonblocking IO, In C, you can basically set a socket to be non-blocking. In Ruby, it's a little easier because you have the dash underscore non-block methods like read non-block and write non-block. And they aren't waiting. They just put the data into the buffer and exit. They don't do anything else. And instead of blocking, instead of waiting, they will just throw an error. So you have the exception. You could catch E again and will block depending on the context, which would tell you that this non-blocking operation wouldn't pass. Of course, for that you would need to test the readiness of the socket in a separate call. But thanks to this, you are able to handle all the I/O in a single thread, in a single loop. Testing readiness, the easiest way is to use IO select, which is a system call in most operating systems. Basically, you pass some arrays, reads, writes, errors with some timeout. And if something gets ready, the select returns with the data. If not, you will wait for this timeout. And basically, that's all. In the game, if you would like to look how it handles stuff, so you implement an event loop that goes through the sockets. This is a dynamic array to which you can push data using the register method. Here you select the sockets and iterate through each of them and write it to the screen. This single thread or single loop can handle a couple connections at the same time. Here it's getting harder, so I need some nodding faces that you get it. Not you, Aaron. Sorry. So this is really great, but it doesn't really handle dependencies. And by dependencies, I mean we need bidirectional transport, and we need to read from one and write to the other one. So a naive implementation of a proxy would look like this. You have an A socket and a B socket, and it's paired to the other one with a method for translation. And you call the IO select in a loop for both the read and the write stuff. And you iterate through the read. And you get the write and translate method from the pairing structure. And if the writes doesn't include the write from here, you need to skip because the other endpoint isn't ready. And here it comes from dependencies. And then you do the same transmission as before with read non-block and write non-block. The problem is that these two lines can cause a spin lock. So if socket A is ready for reading, but not ready for writing, and socket B isn't ready for neither reading, neither writing, then this IO select will return you a single element array here with socket A, and here you will have an empty array. This iteration will jump in, get the write here, but the writes doesn't include this write. So you will jump out from the loop here. You will do the IO select again. You will get socket A only, and you will cause a spin loop, an endless loop, until something else gets ready. OK, nodding faces. Thank you. So this is bad. You wouldn't want to use it in production. We had it for 2 years. And I knew about it. So I was looking in those 2 years for alternative solutions. Stuff like quitting my job or not using Ruby, passing the responsibility to a language or another person, doesn't matter. You could use threads with blocking IO, but if you have 500 connections, you need 1,000 threads. That's probably bad. I haven't tried it, but I suggest you try it if you don't believe me. So it's not good. You could use libraries for asynchronous I/O like Celluloid or Event Machine. They are nice. They work in a sandbox, but in the moment I try to use it in our application, which uses Postgres in an async manner. They all crashed. So those two were no-go for us, even if you have like a single application, they will work. Async is a really nice tool, and I heard that someone here in the community really likes it and likes playing with it. But that time when I was trying this stuff, it wasn't existing, and now I would write it in async. But if I would write it in async, we wouldn't have this talk. So also I was looking into auto fibers, which is a new the next cool thing in Ruby, where you would have fibers, which I wouldn't explain much deeply. They are like cheap threads, where you could yield the context on your own. So the fiber runs, and when you call a yield method, the fiber stops running, and you can run another fiber. Auto fibers are basically automatically yielding when you're waiting on a sleep or a select. Basically very similar how Crystal implements stuff with spawn. They would be really nice to have. And I imagine having fibers something like this, really similar to the threads. So with the threaded method that you have an auto fiber, you put it into an array. The same here is the same transmission from the previous examples, and run them each in a loop. And if a new connection arrives, you can just put 2 new fibers for each. Problem is, and it's basically magic, because you have blocking IO here, but somehow the Ruby scheduler, whatever, I'm not sure how Mets will implement it, will make this non-blocking at the end. Problem is that it's coming in Ruby 3, probably. So we cannot wait for that long. And we came up with a colleague with the idea of bouncing select. And it's basically making the arrays, what we test for select, dynamic. And this is the code with the bouncing select adjusted. I will mark you the lines which are new in the code base. So here you have like dynamic arrays which to read and to write. And after the IO select returns some data, you remove the ready sockets from read and write. And after the transmission, you put them back. So if you imagine again socket A being ready and nothing else, then this select will return with socket A in an array here. It will be removed from the toRead. You will get through the loop. In the next, you will get to the second select again, but here the A isn't anymore because we removed it here. So it will not be in the toRead until a successful transmission puts it back. I will give you some time. And feel free to ask questions. Dima is nodding, but he already knows. Yeah. Which read write? Yeah, this one. Yeah, it should be. Yeah, thank you. Yes. So this is. It should be RDs and VRs. So these are typo. Sorry. So imagine you have different letters here. Anyway, does it make sense? You have a dynamic array, something gets ready, you remove it from the array and select again, and it doesn't happen. You will not have the spin lock. It's still not ideal because IO select is slow. So anytime you call IO select, it sends all the sockets to the kernel. And if you have 500 sockets, you need to copy those 500 sockets to the kernel memory and then call the select, and it takes a long time. And if you do it plenty of times, it's a waste of resources. So I was looking into what the operating system developers were doing in this area. And you maybe heard about EPO. It's basically they split up the passing the sockets part and the actual waiting into 2 separate calls. So first you can register your sockets into the internal structure of the EPO, and then in a separate call you can call for the waiting. So if you call it like repeatedly, you don't have to pass the sockets all the time, so it's much higher performant. Unfortunately, it's not available in Mac. They have something called KQ, but and they are saying it's similar. I have had some problems implementing it on Mac, and we don't really want to support Mac for Manage IQ. So we were just falling back to IO select. But the good thing about EPOL is that it supports this special flag called equal one-shot that will allow us to remove the socket automatically when it becomes ready. So if I show you again, this part of code, which is actually typo, sorry, doesn't have to be here when you use the equal with equal one-shot, because it's automatically deleting any ready socket from the structure. So you still have to rearm it, but unregistering is automatic. So I'm going to show you some C code, how it's actually implemented. Unfortunately, none of the Ruby libraries wrapped around equal support equal one-shot, so I had to implement my own. So here is my register function, which registers a Ruby socket into the equal structure somehow. And here you have the equals one-shot flag, which is getting sent to that equal pointer. And here is my version of equal select equal wait, where you call the equal wait on the equal, you get back some events, you iterate through the events, and imagine a Ruby structure where you update the readiness of these sockets, and then you can iterate through them. It works well on Linux. For any other platforms, it can fall back to IO select. And if you would like to implement support for KQ in Mac, feel free to contribute. You have to do some memory allocation. The good part on Linux, you don't have to do it. On Mac, KQ works a little differently. So you have to play with Walgrind and malloc and free, and I will be happy to merge it. So the second chapter, WebSockets. WebSockets are not TCP sockets on the web, as some people would think. They are basically abusing, WebSockets are abusing HTTP for bidirectional data transfer. So you open an HTTP connection, and then you use it for a different protocol. So if you have a browser and a web server, the browser sends a request something like this. So it sends the connection upgrade header and the upgrade WebSocket header. These two headers were originally intended for upgrading to newer version of HTTP, but also WebSocket RFC implements it. So the web server sends back switching protocols response to WebSocket, and then the whole communication is a different protocol defined by this specific RFC, if you want to read it. If you think about how this could be implemented in Ruby, so Ruby web servers are implemented in Rec, and if you look at Rec, this is a simple example. I added some comments from the website of Rec. So you have something that responds to a call method, which yields with an env, which basically is your context of the request, so like headers, cookies, session, and all the other stuff. Here you can do some logic, and at the end you have an array of 3 elements, 3 items, the status, the headers, and the body, which is returned. And anytime a new request comes in, this handler runs this function or lambda or proc or whatever, a class that responds to the call method with your request. So it's basically a function as a server. No lambding. So if you think about this, this is not really good for a persistent connection, because you don't want to get stuck here, because then you cannot handle the next request if you're having just a single thread. So to overcome this, the developers of Rec implemented socket hijacking. Socket hijacking is a technique where you can ask the server for the socket to give it to you and don't care about it later. This is from a movie where guys saying hijack. There is a guy and everyone's saying hijack to him, and he's giving not a fist bump. What is it called in English? Okay, and there is a robber and hijack hi and shoots his leg. Anyway, so socket hijacking. So socket hijacking is marked here. You have in your env hash a proc or a lambda that you can call, and it returns you a socket. It's an actual code example from our application. So you have a proxy in a separate thread. You have a lambda. Here you can test for HTTP. I will not show you this method, sorry. And here we have a magic function that returns from the env an address and a port to the remote endpoint I was showing in the previous slides. Open a new connection to this and put it into the proxy for WebSocket and VNC. And we return with something for rec so it wouldn't crash. So a request goes through this flow really fast, but actually the socket gets passed to this proxy out from this context, so the rec server can handle your next request really fast. And this is how our stuff works. So you have your browser, you do the hijacking, and then you do the translation with the proxy. And does it make sense?
Did you implement proxy?
Yeah? This one, yes. There was another one in Python, but that wasn't as good. So I was promising some smuggling, as I told to the border guard in Australia. So when I was playing with these requests, I was thinking about what if we upgrade to something else? Will it work? And I was playing with a little, and yes, it will work. So I was happy that I could do something nasty. So here is the original architecture, and I was thinking about something like this. So instead of the browser, you would have a client proxy and a desktop client with a VNC client that could connect to this client proxy and use some crazy HTTP to get through the proxy, which is an HTTP server, and get to the VM. So through a restricted environment, get through your VNC client through this whole thing. And you would ask me why I am doing stuff like this. And the answer is simple. The browsers are slow. If you ever tried to render a Windows desktop on an HTML5 canvas, you realize that there is no clipboard, there is no key mapping, and the user experience, animations, and things like that aren't the best. So we would wanted to provide our customers something more smooth. So as you know, there are two hard problems in computer science, cache invalidation and naming things. So I came up with a name for this thing. And I think you all guessed it stands for Protocol Upgrade Raw Request. Which is basically HTTP upgrade, downgrade to TCP and use VNC, or SSH, or whatever protocol you want. It's basically a TCP session smuggled through an HTTP connection. And in action, it looks like this. You have a cluster of virtualized cluster here, Manage IQ, our product, running separately, running with the proxy. It's embedded in the Rails server. And your browsers, you click in the browser to a native console instead of a remote console. You send a request to the server in its own language. You want to purr like a cat or whatever you want. It sends back, you go for it, talk to purr MIQ. A browser, based on this protocol, it triggers a plugin. The plugin says, I'm listening on localhost 1234. The browser displays this information. Please point your favorite client to localhost 1234. You open your favorite client and you point it to localhost 1234, which sends it to the plugin. The plugin, that will be VNC. The plugin opens an HTTP upgrade connection to purr to the web server, which is actually going to the proxy, because there is a Rails route here. You get back an HTTP 101. And you have your protocol here. And the proxy on the other side does the same with the previous example. So it opens VNC, and through this cool blue thing, you have a tunnel to your VM through an HTTP connection, bypassing any firewall here. So there is one problem with this. The plugin cannot really open a TCP connection in the browser for now. Actually, there is a draft from the W3C which isn't yet accepted. So you need a browser plugin and a native binary, which is actually supported. So you can ship to the clients a native binary with the plugin together and run it from your browser. I will show it later. I have a demo. So the architecture looks like this. So you have a server, as I explained it, the proxy. There is a plugin that actually calls just this client proxy, which is the binary. And we would need a front-end library that is not written yet because I'm not good with JavaScript. Feel free to help. The server usage of the server is really rec-like. You define a lambda, a block, where you implement your own magic function that gets back a host and a port from the env. That would be your remote endpoint to where you want to smuggle the things, and you run it with rec, or you put it into a Rails route, whatever you want. A really good thing is that it behaves like HTTP. So you can have all the rec middlewares for logging, routing, authentication. You can use cookies. You can use HTTP headers for setting the parameters where to send the smuggled things. You can use HTTPS. And for now, the only disadvantage I see is you need the browser plugin and the binary. But that might change in the future. So it's really far from production ready, but it works. And I would like to show you a demo. Okay, I will stop the mirroring. So here I have that's the Vagrant build I showed you before. This is the Vagrant file I ran. So you have a Docker installation, a CentOS software collection, GCC, make some dependencies. Don't ignore this line. I'm running two containers. One is running XFCE VNC server with some resolution with a demo password, and an SSH container with my keys already enabled root login. And I install Ruby, I install Perl, my stuff, and Puma. And I set up some hosts to the IP addresses of the two containers. The server I'm running looks like this. So I'm running puma per.ru, which is this server. I'm serving a static file through rec-static, and this is my per server. When the URL is VNC, I'm sending the client to this host and port. If the server is URL is SSH, I'm sending it to this server and this port, VNC and SSH, and I'm running the app. The static HTML looks like this. So I'm dispatching some events to activate the browser plugin with the URL, which is either VNC or SSH, and I'm displaying it in the browser. So if I SSH into this machine, this virtual machine, here you see the addresses of the containers. If I try to ping it from here, it works. If I try to ping it from my machine, it doesn't work, so I don't see the containers. Does it make sense? Okay. So if I try to run this command, which will start the server, yes, and point my browser into this address, 9292, the default rec port. Here I have a per demo. I can start a VNC session. It tells me to point my browser to localhost this port. VNC client. My VNC client is prepared. I type in demo. And here I have a connection to a container from my machine, which isn't accessible from my machine through HTTP. And if you have performance questions, there is no sound. Maybe better. Also, you can do SSH. So if you do, sorry, Rick. So if you do SSH to this port, my key is already there. Sorry, I might need to zoom in, right? Zoom in, zoom in, zoom in. So I'm connecting to that port, I accept it, and I'm there. And this is that machine with that IP address in the container, SSHing through an HTTP session. Thank you.
Thank you. Yeah, we have time for like 1 question, 2 questions.
I have some stickers for the people who ask questions.
Okay, I had 1 question, but I forgot it. I didn't know.
There is 1 question.
Will you share this code and presentation somewhere? Okay. Okay.
I can talk without words, you see?
David probably will share slides
Yeah.
on Twitter, so you can check.
There is 1 question.
Hello, thank you for your story. I want to ask you, why did you rewrite all these things from Python? Why Python is not so good?
The problem with the Python thing, this original WebSocket to socket proxy, let me back to that. Maybe I shouldn't use the clicker. This one.
Yes.
Yeah. So this one in Python, the problem was that the Python thing was just for 1 single connection. So you had to fork a new process for each connection. Mm-hmm. I think it makes sense not to use spin up a new Python process for that. So I can send you the link for the Python proxy. It's just like 50 lines of code, and we didn't want it. We wanted it in our Rails environment as tight as possible.
I saw it very closely. Okay, thank you very much. And 1 suggestion from guys. We're a little bit waiting for WebMKS console, not in standard manager queue, but in CUI. WebMKS console.
Oh, you are the people who want it.
Yes.
Yes, I promise. I'm bugging the person who needs to write it. So.
Okay. We are waiting. Thank you very much.
Yeah, thank you, David.